Okay, and we're live? Okay. Hey guys, welcome to the natHACKS Hardware Intermediate Workshop. I'm Harrison. I'm a second-year master's student in computing science here at the U of A. I've been a member in NAT for about 3 years. I've mostly been on the project team side of things. Right now I'm in the Hackathon project, which is, we're working on building a neuroprosthetic, so a neuroprosthetic hand that you can control with EEG signals. Just before I start, I guess, going into the presentation, during this presentation I will be sort of bouncing between slides and a code notebook that has code snippets. So if you don't have that already, you can just go to nathacks.ca/ws2, and that should link you directly to the notebook. And there's two ways to run that. The first one, which I suggest, is through Jupyter Notebook, but you might not have that installed already. And the other one that's just immediately available to you is Google Colab. So you can just run it straight off Google. And the downside to that is that it's not doing anything locally, so you can actually connect it to your device, but there is a synthetic device that I have in it, so it should still run. There shouldn't be any errors. It's just if you actually have a hardware device you want to test, it won't work with that. You'll have to run it on Jupyter Notebook. So what will we actually be going over today in this presentation? We're going to be focusing on BrainFlow, which I'll go over what that is soon. So we're going to talk about what BrainFlow is. Then we're going to talk about how you can install BrainFlow on your device. Then we're going to talk about how you can connect your device to BrainFlow, and then how you can read data from it, and then how you can use some of the pre-processing functions that BrainFlow has built in. So let's get into what BrainFlow is. So BrainFlow is a model-agnostic package that has a wide range of supported biosignal devices. So by model-agnostic, I mean that not only does it support a bunch of biosignal devices, it treats them all essentially the same. So that means you can write some code for some device, and usually with only having to change maybe 1 or 2 lines of code, it should run for another device. So I had another project I had set up for the OpenBCI, and I was having issues with it, and I wanted to test it with the Muse, and I only had to change 2 lines, and the entire thing just still ran completely fine. So it allows for reading data from EEG devices, but not only EEG devices, it also supports EMG, ECG, EOG, so a bunch of non-brain signals as well. It's not just for brain signals. And some devices have both EEG and another biosignal, and it does support both of those simultaneously. A really handy thing that BrainFlow has that I use a lot is it has a synthetic device. So it's basically, you can set up an object to connect to your device, but if you don't actually have a device available, or you have errors, or you don't want to go and put in the effort to set up your device, you can run a synthetic device which prints out just fake data that kind of looks somewhat like brain data. It's pretty sinusoidal, but it allows you to be able to test your code for your EEG device without actually needing an EEG device. And BrainFlow is available in multiple programming languages, like Python, C#, R, Java. I think there's maybe at least six different languages it supports. We're going to be focusing on the Python implementation, however, today. But the resources are available on the BrainFlow documentation website if you do want to use it in another language. So some of the supported devices that are going to be relevant to you guys, it supports all of the OpenBCI headsets. It supports all of the Muse headsets. It supports the G-Tech Unicorn. And there's a few more which, there's a big list. There's I think 40 or 50 different devices that it supports. I don't think it supports the NeurAlbertaTech Arduino though, which is one of the other offered hardwares for natHACKS. So let's now talk about how you can go about installing BrainFlow. So the first thing you need to do to install BrainFlow for Python is you need to make sure you have a somewhat recent version of Python, greater than 3+, so Python 3 point something, you should be able to install BrainFlow. And to do this, it's pretty easy. If you're on Windows, Mac, or Linux, I believe it's the same. You should be able to go into your terminal and you just type the following command without the parentheses. But if you do have the code book installed, you shouldn't have to do this. I have I guess I'll go over it real quick. In the actual notebook, the first thing that I have, this snippet actually installs all of the libraries. So if you're on Google, it'll install it for like the Google virtual machine or however it runs it. If you're running on Jupyter Notebook, it will install it locally. But yeah, you should be able to run all of this fine, even if you don't have the packages already installed. And then in addition to installing BrainFlow, there's 2 other libraries that we're going to be using that are pretty useful. The first one is NumPy, because the output of the brain signal, like when you read the data in, it comes in a NumPy array. So you want to have NumPy installed so you can use any like matrix or array operations on it. And it's a generally like pretty useful like library to have. And the second one is matplotlib, which just allows you to make sort of graphs and plot out your data that we'll use to visualize our data in the notebook. And those are also installed right at the start, similar to BrainFlow. Oh, am I good to move on? Okay. And again, you can install BrainFlow in other languages. I won't go over how to do that, but if you go to the BrainFlow documentation, you can just Google BrainFlow and all the docs pop up. But if you're on the BrainFlow site, right on the side, you'll see installation instructions, and they have installation instructions for Python and C# and a bunch of the other languages. All right, and now that we have BrainFlow installed, let's talk about how we can actually connect our hardware. So to be able to connect your device to BrainFlow, you need to have 2 pieces of information. The first one is you need to know the board ID, which is pretty easy to find because all you have to do is if you go to the BrainFlow documentation, under the user API, the very first thing that sort of shows up is these board IDs. So when you're here, you want to find the name of your device. So in this case, I'm using the Cyton Daisy, the OpenBCI Cyton Daisy. So I can just see here, Cyton Daisy board, the ID for that one is 2. And then another, because these are enums, enumerators, that means within the BrainFlow library, if you import, I guess I'll go over the importing later, but if you import board IDs, you can just do board IDs.cytondaisyboard.value, and that's the same thing as just typing 2. So there's 2 ways to do that. And the second thing, which is a little bit trickier to find out, is you have to find out the serial port that your device is connected to on your computer. So on Windows, this will look like COM and then followed by some number. If you're on Mac or Linux, it should be, it'll look like /dev/tty and then followed by something. So the way you can find that is if you're on Windows, you can open your device manager, and if you show hidden devices, I think you can actually skip the show hidden devices. I think it should work without it typically. If you go to the section that has ports, COM and LPT, you can find your device. And then it'll say what COM port it's connected to. So I'll quickly show you how to do that because I am on Windows. So if you open your device manager, and then at the top you can click View and Show Hidden Devices. And we've got this section here that says Ports, COM, and LPT. And if you open that, you can see it's got all these different sort of devices. But the only USB serial port, because I am connected via a USB dongle to the headset, the only one that's like non-grayed out is COM5. So COM5 is the serial port that my OpenBCI is connected to, and that's the one that I just enter here as the serial port. Okay, and then I'll show you how to how you actually go about using the serial port and the board ID to actually initialize your board.
Wait, do you mind showing the one to get to the Jupyter notebook?
Oh yeah, yeah, sure.
This one to get to it?
Like the URL?
Yeah.
Yeah, it's this one right here. So nathacks.ca/ws2, and that should link you like directly to.
It says something has gone wrong. The issue trace is no.
Uh-oh. Let me see, because if I, oh, that's new. I was working like a couple hours ago. That makes things a bit tricky. I guess did you guys receive any like email or notification with the notebook? I think, okay, that wasn't sent out either. Well, I guess hopefully that should be fixed soon, or fingers crossed. Yeah, but it should be available at least like some point before natHACKS, so you can still have access to the code and use whichever snippets are useful in your projects.
Try again.
Let's see. Okay, yeah, that works now. Yeah, so if you get to this, you can either just download it, and then if you have Jupyter Notebook, you can just run it like that, or there should be, like at the top, it should either say open with Google Colab, or you can go into like the connected apps and should be able to just run it with Google Colab. And that'll just open it like this. Okay. All right. So the first thing that we're going to do is I'm just going to run the code. I already have these installed, but I'll just show you sort of what it looks like. So if we run this, it'll install all the libraries that we're using. So because I already have them, it says like requirements already satisfied. But if you don't have them, it should go through the install. It shouldn't take too long, maybe like a minute or two. And then what we're doing here is we're just importing the libraries we're going to use. So there's two parts of BrainFlow that we're going to be using. The first is the board shim functions, which is all related to the actual device itself to be able to like read and write from the device. And the second one is the data filter side, which is the pre-processing stuff we'll be going over later. And then we're just importing NumPy and Matplotlib. I'm just renaming them to NP and PLT, so if I use those later, that's referring to NumPy or Matplotlib, just to sort of shorten it so I don't have to type the full name. And then finally, we're importing time, which just later, so we can just like wait a few seconds before getting the data. So what we're doing here is now we're actually going to enter our serial port and board ID to initialize our device. So what we do first is we create a BrainFlow input params object, which stores a bunch of parameters related to initializing your device. But the only one we're really interested in, the rest are going to, most of them are just going to be the default settings, which are fine. The only thing we have to change is the serial port. So we've got our params, which is the BrainFlow input params object, and we just do .serial port. Params.serial port equals, and then you enter your serial port, or actually, sorry, I forgot to go over real quick. I only went over Windows. So to find your serial port, if you're on Mac and Linux, you can just open your terminal and you type ls/dev/period*, and that should list all of the devices that are that sort of like match that I guess path, and then you should be able to spot your device in there, and it should say the name of it, like the name of the serial port it's connected to, similar to on Windows. But yeah, so you enter your serial port as a string, and then to enter your board ID, you just can either have it as an int, whatever the board ID value is, or you can do board IDs dot and then the name of the device as shown on the BrainFlow docs. So for example, if I wanted to use like the Muse 2, I would just do board IDs dot Muse _2 _ board, and that's the same as, again, typing 38 instead of all that. So here I'm just going to run these and initialize these values. Oh, it was on the wrong one. On this one. Okay, and then I print the board ID. So again, this whole thing is just equal to 2. So you don't have to go to all this effort. You can just type 2 if you want. All right, and now we're going to actually like connect to our board and initialize our board object. So in this snippet, the main part that we're going to sort of pay attention to first is just here. So the first thing I'm doing is I'm just making sure that the board ID I've entered is actually equal to the board ID I'm interested in. You could probably just get rid of this line. Actually, no, keep that line because I do change the board ID if it can't connect properly. But to initialize or to create a like device object, we create a board shim object and we pass in 2 parameters. The first one is just the board ID, so just the int for our board. And the second one is our params, which is again the BrainFlow input params object with the serial port. And then once you've got that, to actually like initialize your device and make sure to like actually connect to your device, you call board.prepareSession. Now this line is probably going to, like, if you're going to run into errors in anything, it's probably going to be from this line. If your device can't be detected, like it's not connected properly, it's going to throw an error. If your device is being used by another program, it's going to give you an error. If you've already prepared a session, like you've connected to your device and you try to connect to it again before disconnecting, it's going to give you an error. So there's a lot of things you sort of have to be careful with this line, and just pay attention to the error message. So I've got there, so it's in a try and except clause. So that means if it does throw an error, what we're going to do is instead of using the OpenBCI device, we're just going to use the synthetic device that I mentioned earlier. So all we have to do for that is we just change the board ID to that of the synthetic board, which here the synthetic board ID is just -1. So it just changes to that, and then we can just initialize the device the same way. So with the synthetic device, you don't actually need the serial port because it's not connected to anything. It's just fake data, but you still have to pass in your params object. And then it calls prepare session again to connect to the fake board. And then lastly, I've just released the session. So this part is basically just connecting to the device and making sure you can connect to the device. And then we release the session so that we can sort of like reconnect to the board later. So if I run this, it should, oh, that's because I do not have it plugged in. Okay, so now that the device was off, so it says board not ready, and then it's created a synthetic device. If I just go and I just sort of reinitialize stuff and I run it, there you go. So now successfully prepared physical board. So this is working and connected. All right, and now that we've I guess connected to it, we can talk about reading data. But before that, does anyone have any questions? Okay, and then if anyone in the chat has any questions as well. Okay, no questions from the chat. All right, now let's talk about reading data from the hardware. So there's a few small things you should know before we start reading data. So the first thing is that, as you may know, EEG devices record samples at a mostly consistent frequency. So the reason I say mostly is that some EEG devices send out samples sort of in packets. So instead of just sending out one sample at a time, they might sort of like collect them and then send like 2 to 4 samples. So depending on where you stop your recording, there might be like slight differences in the number of samples. Like it might not be exactly the amount of samples you expect. And as far as like the frequency, so the OpenBCI records at a sampling frequency of 125 hertz, which means that every second it outputs 125 samples. Another thing is that BrainFlow, the data that it records is in microvolts. So that's something that you have to keep in mind if you're going to be using the MNE library, which I'll sort of mention lightly sort of towards the end. But you have to sort of be aware of kind of the units of the data that you're working with. And another thing is, as mentioned earlier, BrainFlow not only records EEG data, but it also records other biosignal data. So if you're just interested in EEG data, you have to isolate those channels, because when you get your output, it's going to have a bunch of channels, and a lot of those, or some of those, will be like other biosignal data that's like non-existent. So you can just get rid of those. And BrainFlow stores samples in an internal buffer when it's like reading from the device. So when it's reading, it's just like it's saving those samples that you can access later. But some of the functions, when you call them, they take all the data out of that buffer, so they leave the buffer empty. And some of them just leave that data in. So you have to be careful and read sort of the documentation for the function you're using, whether the data, whether the buffer is sort of being like copied from or just directly taken from. Because if you are just copying data from it and you're calling that too often, you might be like accessing old samples. So you want to make sure you're not like sampling or taking data faster than the data is being like output from your device. And then the last thing is that we can insert markers into the recordings to identify exactly when the stimulus appeared. So that means if you have some sort of event or stimulus associated with your data, or when you're recording, you can insert that into the data stream, so you can pinpoint the exact sample at which that like event happened. So you don't have to like manually calculate the like which sample. You don't have to try to, I guess, estimate or approximate which sample the event happened at. You can tell like which exactly, when exactly it happened. So now let's go back to the notebook and actually start reading some data. So this is a, I guess, very simple snippet where we just read 5 seconds of data from the board. So the first thing that we do is we prepare the session as earlier. We connect to the board, and then we start the stream. So what this does is it just tells the board to start, I guess, giving data to BrainFlow, and BrainFlow starts storing it in the buffer. And then we call time.sleep 5, which just means we just wait for 5 seconds. We just do nothing and wait for 5 seconds as data is being like accumulated. And then after the 5 seconds is done, we call board.get_board_data, which this one actually takes all of the data out of the buffer. And then after that, we just stop the stream, and then we release the session. So I'll just run this, and we'll let it run. So it started the stream, and now it's just waiting 5 seconds. And then it's ending the stream. So now in data, we have our all of our data from our board that just got streamed in that 5 seconds. So if we go and we actually look at this data, right now, right here, I'm printing out the data type and the shape of that data. So if we look at that, we can see it's a NumPy array, and the shape of it is 32 by 602. So that means we have 32 channels, and for each of those channels, we have 602 samples. And this OpenBCI, it only has 16 sensors. So as mentioned, we have to trim some of that off because there isn't actually 32 channels that we're interested in. So to do this, we can first find out which of the channels are EEG. So to do this, we can call board.get_EEG_channels, and then you have to pass in the board ID again, which I'm not sure why you have to do that because it should be saved in the board. But if you do that, that gives you a list of the indices of the channels that are the EEG data. So, and then what I'm doing after that, after I get the EEG channels, is I'm isolating those channels from the data. So because this is a NumPy array, it has a useful feature in that you can index it using a list. So I'll just quickly run this. So we can see channels 1 through 16 are the EEG channels. So in Python, array indexing starts at 0. So channel 0 is an EEG, but channels 1 through 16 are EEG. And if I index all of the data just by those EEG channels, it's just going to give us those 16 channels with all their samples that we're interested in. And then if I print out the data, it's just going to sort of show you sort of what the data looks like. I guess I wasn't wearing it, so it's sort of just nonsense data. But yeah, so all of these are in microvolts. So it's basically, the array has like 16 sort of sub-arrays. Like each row is a channel, and sort of each column is a sample, so yeah. And another thing you can do is you can find, I don't think this is going to work probably, but I'll try running it. You can, much like you can get the EEG channels, you can get the other channels. So if I run this, I think, yeah, it's going to say, this is wrong. For some reason it says channels 1 through 16 are EEG channels, but I think it's because this OpenBCI is only EEG. For some reason it's outputting that, so I guess you can ignore that. But if you have like some device that does have other biosignals, it should work, hopefully. I don't know, I haven't really worked with devices that do multiple data types. And then right here, we're just going to plot out the data from the first EEG channel across the 5 seconds. So all the data just from one of these sensors. So I'll run that. So yeah, so over the 600 samples that we recorded, we can sort of see the pattern that it follows. I'm actually going to quickly re-record the data because I wasn't even wearing the headset. So I'll put it on. We'll see if this gets more like real-looking data. And then we'll get the EEG channels, the EEG data again. Okay. Now if I run this, okay. So that's what one of these sensors, that's what a part of my brain apparently looked like over those 5 seconds. All right, and as mentioned earlier, you can also insert markers into your data to pinpoint when like different events that during the recording happened. So this is pretty easy to do. All you have to do is you just type board.insert_marker, and then you pass in the value of that event that you want to show up in the marker channel. So I'll just quickly run this. So what this does is it's pretty similar to before, except every 1 second it inputs a marker with the value of like that second. So I'll just run it. So it's starting the stream, and then we can see it's inserting these markers. Okay, so we've got our data. And again, much like we can get our EEG channels, we can find which of the 32 channels that has the markers. So if we just run this, we can see that at index 31, that's where the markers are kept. So the very last channel. And then if I print that out, so if I just index all of the data at the marker channel index, it'll give us just the marker channel. And if I print that out, so because there's 600 samples and we only input five markers, it's going to be mostly zeros. So when nothing's happening, the default that BrainFlow puts in is like a 0. So you have to be careful that when you're like inserting your markers, don't use 0 to represent one of the events, because it'll just be like nothing but zeros. So we can see like hidden in our big sea of zeros is we've got that first marker right here, a second marker is here, and they're all hidden in somewhere. But rather than just like trying to count and look at it directly, what I'm doing here is using a NumPy function called mp.nonzero that tells us the index of any samples that don't have a value of 0. So it'll tell us where all of our markers appeared. And then after that, what I'm doing is I'm getting the sampling rate from the board. So I'm getting the frequency that the board records at. And then lastly, if you divide which sample number the event happened by the sampling rate, so the sample divided by how many samples you're putting out per second, it'll tell you at which second the event happened. So I'll run this. I was testing it earlier and I don't think it, yeah, I don't know. Okay, so it's saying that when we inserted the first marker, it happened at sample 60, and the second one happened at 240, and so on. So if we work backwards, we could find out when these markers were inserted. So there's a weird thing happening here. For some reason, because the OpenBCI, it records at 125 samples per second, and we inserted the first marker after 1 second, it should be at like 125 or a bit after. It's at 60 for some reason. I haven't had time to sort of figure out why. But the first marker got placed at half a second in. I think this is an issue of the board not recording like at a constant frequency. So that's something, again, you have to be careful with. But the second marker was placed close to 2 seconds. The third marker was placed close to 3 seconds. So the rest of them are fine. For some reason, the first, I think it might have just like, actually, I will try something real quick, because the device might need to like warm up. So I'm just going to let it run for a second, and then I'll start inserting markers. Because yeah, it might have just been sort of a bit slow and not outputting all the samples at the start, and then once it's been running for a while, it does. So I guess we'll see if that happens. So we print. So if we print the markers, and then if we do that. No, that is weird. OK. So yeah, again, it happens like half a second later instead of 1 second. That's a weird issue. I'll have to figure that out later. But basically, you can find out which sample. So it is correct that that marker happened at that sample, but like the time that it happened is not correct. And that's because I've, I guess, calculated it myself instead of using the brainflow functions. And then the last thing that we'll talk about is, because what we've done so far is we've recorded our data, and then we'll stop the stream, and then we'll sort of like grab the data. What you might want to do is you might want to read the data live. So while you're recording it, you might want to be able to access the data. And this can be done by calling board.get_current_board_data. But what you have to do here is you pass in as a parameter the number of samples that you want to take out. So what this does is I put 25. So that gets the 25 most recent features from the device, and it leaves them in the buffer. So this is the, I guess, like function you have to be careful with, that you're not calling it too often, because then you're going to have like overlap between your EEG signals, or like the samples that you're taking. So what I'm doing here is every second I'm just grabbing 25 samples. So if I just run this. Okay, so yeah, every second it's grabbing those 32 channels with 25 samples. And yeah, and then that data will just look like sort of all the other data. Yeah, so yeah, when you do call get board data the other way, that's just grabbing all the data. You don't have to specify the number of samples you want, but in this one you do have to specify the number of samples that you're grabbing. Okay, and that's about it for actually like being able to read data from your hardware. I guess, does anyone have questions about that part? Okay. All right, and now lastly, we can talk about some of the pre-processing functions that BrainFlow has that you may want to use. So BrainFlow has, I say many, but I don't think it's not too many functions compared to some other like libraries out there. But the ones that are probably relevant for you and are probably the most commonly used ones is a low high pass filter, so that removes like the low and high frequencies. There's downsampling, so that sort of reduces the number of samples that you have. It like sort of squishes them together. And then there's the wavelet or fast Fourier transforms. But because the data is in NumPy format, which is like a very common library and a very common format in Python, there's a bunch of other libraries that you can use to do these kind of functions or other like EEG or signal processing stuff with. So one of those that's pretty useful is MNE. But to use it in MNE, you have to do a little bit of sort of playing around and changing the data and sort of inputting some values to be able to use MNE with it, but I will go over that after. Okay. All right, so the first thing that I'll show is how you can save the data. So BrainFlow has its own built-in function for just saving and writing your data, which like you don't really need to use BrainFlow's version because it's just a NumPy array. NumPy has sort of its own version, but you can just call data filter, which was imported at the start. We've imported the from BrainFlow.dataFilter. We've imported the data filter functions. And on your data, you can call datafilter.write_file, and then you pass in your data. So I passed in my EEG data, and then you pass in the path and the file name that you want. So in this case, I'm just saving it wherever I'm running Jupyter Notebook. That's just going to be where it saves this data. And I've called, and the last one is like the mode of how you want to write. So in this case, I've got W, which means you're just going to overwrite any file that you have. If you put an A, it'll append. So if you've already got a like CSV file, it'll just add to the end of it. It'll just like add more data. And then after you've written your file, if you want to read it back later, you can just call datafilter.readFile. And for that, all you have to do is you have to pass in just the path to the file, the same as like when you wrote it. And then that returns a NumPy array. So you have to actually save that to a variable. And if I run this, I'll just show. So what this does is it writes the file, and then it immediately reads it back. And then I'm just showing you the difference in the data between the original file and the file that was read back. And this is just showing there's just, like they're not exactly the same, but there's very small differences. So you shouldn't really have to worry about it, but they just can't be treated as like the exact same like array. As far as the filtering goes, this is how you apply the low and high pass filtering. So first, I'm just going to record some data. This is also inserting markers. That doesn't need to be done. But what we're going to do is we're going to apply both a low pass and a high pass filter to our data. So you have to apply this filter to each channel separately. You can't just apply it to the entire array, as far as I know. So what we're doing is we're iterating over all the channels, all 16 channels in the EEG array. And then we're performing a low pass. So for that, we're passing in our EEG data to the like datafilter.performLowPass. And then you also pass in like the sampling rate. And the last of these are a few just like low pass filter sort of settings. And then we're doing the same thing with high pass. And something to note with this is that these functions actually change the data in place. So if you want to have the data before you perform your low pass or your high pass, you should make a copy of it, or you should apply this to a copy of your data, because it will edit it. So I'm just going to quickly run this. OK, so this was the EEG data. I wasn't actually wearing the headset, so this is sort of just nonsense data. But this is how the data looks before we do any filtering. And once we remove like the high and low frequencies, it looks something like this. So we can tell it's done something at least. And again, yeah, that is done in place. So I don't actually change the EEG data like directly. I don't like change it to, I don't assign it to anything else. It just changes it in place. Okay. And then for the wavelet transform, it's kind of a similar thing. You have to apply it to each channel separately. But for this one, it's not changed in place because it's like, I don't know, it's a bigger transformation. So for this, you call datafilter.perform_wavelet_transform, and you pass in again your EEG data of the channel that you want to perform your wavelet transform on. And then the next parameter that you pass in is the type of wavelet transformation that you're interested in. So what like mother wavelet you're interested in. So there's the documentation on this is pretty. It's kind of incorrect from when I've been messing around with it, because it says you pass in like a wavelet type. I think it's like a wavelet type like enumerator similar to the board IDs. But when I've tried doing that, it's given errors, and when I've like looked into the actual like source code, it doesn't exist. So there's two ways to do it depending on sort of, I think, what version of BrainFlow. Sometimes it works, sometimes it doesn't. You can either pass in the ID of it. So if we go to the documentation, let's go to the data filter section. Where is it? Okay, so there are wavelet types, which are the enumerators, and you're supposed to just be able to enter like wavelet types.db1 or whatever, but that doesn't work. So you can just find whatever value you've got here. So in this case, I'm performing like a db1 wavelet, so I'm just using the value 1. So you can you just enter that directly. Sometimes that doesn't work. I've had it sometimes where that also gives an error, and in that case, you can enter like the name of the wavelet type, but as a string. So here I've just entered like db1, all lowercase, as a string, and I found that depending on your BrainFlow version, sometimes you need to put it as a string, sometimes you need to put it as an integer. It's pretty finicky, but one of these versions should work. So if you're running this code and this gives you an error, just comment out this line and use the other one, and then one of them should work. And then the last one is the like level of decomposition you're doing, I believe. So in this case, I'm doing 3. So that returns both the wavelet coefficients and lengths. If you want to break it down into, so when you get your wavelet coefficients, there's 2 types. There's approximation coefficients and detailed coefficients. To be able to grab those, you can just, you have to use like the lengths that tells you whereabouts the approximation and detailed coefficients sort of end, like how many of them you've got. Yeah, this might be, I guess, too much information. You might not end up using wavelet transformations, but it is like kind of common as well sometimes. And then lastly, what you can do is if you've got your wavelet coefficients and your lengths, you can actually get your EEG data back from that. So you can do an inverse wavelet transformation. So in this case, we're performing wavelet transformation, and then we're just doing an inverse wavelet transformation on it, and then I'm printing out like the difference in the data before and after. So if we do that, so this is the difference. So it's like to the -11. So these are really small values. So it does a pretty good job of like getting the original data just from the wavelet coefficients. So yeah, so that's useful if you want to like perform a wavelet and then do some more like processing on that and then sort of get the data back. And then one last thing is I mentioned the MNE library earlier, which is it has a wide range of functions that are useful for like biosignal processing or just signal processing, not just EEG, but like a bunch of other stuff. I think it might work with other data types other than just signals as well. But it's a very useful library, so you might want to use it. So for here, I'm just installing it separately. And to be able to convert your BrainFlow data into an MNE like type, you need you need some information from your device and from your data. So the first thing is you need your EEG channels, which you can just get from board.get EEG channels. You need your sampling rate, you need your channel names, which it tells you like which each of these sensors has like a specific name. I'll show later in it'll like put up a montage that has like the names of these sensors. But you need those, which you can just get from get EEG names. You need to know where your marker channel is. If you want to use your marker channel, you can just ignore that otherwise. And then next, what we do is we just we do this EEG channel types, which basically just for each of the EEG channels, we just like have we just have a list that's just EEG, 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 and then the last one will be marker, just so we can sort of so MNE knows exactly which channel in your data is either EEG or a marker. And then what we're doing here is we're changing our data from microvolts to volts because MNE works in volts and BrainFlow outputs in microvolts. And then what I'm doing here is I'm just isolating just the EEG channels and the marker channel. The way I'm doing it is kind of odd. I'm concatenating together the EEG channels with the marker channels into like a list and then indexing by that. But you could just get them separately and then concatenate them together. And then next we create an info object, which is what sort of we pass all of this information into. And that stores all the information about our device and the data. And then we can create a raw MNE object or raw array just from the both the data, that's our EEG data, and the marker channel data, and the like info object that we just created. And then once we've got that, we can we have a like MNE raw object, and we can just perform whatever like MNE like functions that we want. So in this case, I'm setting, or I guess another thing you have to do after that is you have to set the montage, which the montage is just sort of a standard like reference for where the different sensor types on different EEG headsets are. So I just sort of define which montage I'm using. And then you have to set a reference channel, because like all the, when you have your like changes in voltage in your EEG device, it's in reference to something. So in this case, they're in reference to the average of all the sensors. And then lastly, I just plot the data using the, I plot a spectrogram of the, or actually no, it's not a spectrogram. I forget what PSD stands for, sorry. But it just shows the frequencies instead of the, I guess it shows the power of each of the frequencies. I guess I'll run it real quick and it'll be easier to understand. So this is the montage that I was talking about. So it's saying any sensor, like the name of the sensor refers to sort of where on the head it's placed. So this would be like F4 or something like that. And then I also plot out the spectrogram, which shows for each frequency sort of the power of it. Because usually when you're like when you're doing analysis on EEG data, you're sort of looking at like which frequencies are showing up rather than just like the raw EEG data. But yeah, I think that's basically everything that I had to tell you about BrainFlow. There are, on the BrainFlow documentation, if you want sort of more, like this is pretty much all the stuff from BrainFlow that I've ever had to use. But you can go to the user API to find any details of any parameters or functions that you want to use. And then what I find more useful, because the documentation is kind of doesn't have much information, it's a bit messy, is to instead just look at the code samples that they have. So they have, for Python, they have a bunch of different samples which show how to do like things like markers and data, similar to my notebook, but a bit more, I guess, convoluted. But yeah, that's basically everything I wanted to go over. Does anyone have any questions? Yep.
Yes, what are wavelet transforms typically used for?
Wavelet transformations are to, because I mentioned you're interested in sort of like in the frequencies rather than just the raw data. The wavelet breaks it into like which frequencies sort of make up the signal. So it tells you like for each, I guess, frequency band, like the power of it. And that's usually what you feed into like some like machine learning algorithm or whatever. Sort of how powerful each frequency, or how, I guess, how much each frequency is coming up, because yeah, different frequencies are associated with sort of different things in the brain. Is that a decent explanation? Yeah. But yeah, I would suggest if you're interested in wavelet transformation, there's a few like, if you just go on YouTube, there's some pretty like informative videos that sort of make it a lot easier to understand, because it's like a super confusing thing. A lot of like signal processing stuff is pretty convoluted. Yeah. So did the notebook run for you guys?
Yeah.
Like, yeah. Okay. Cool.
For high pass and low pass filtering, what is it filtering out?
Like high and low frequencies. So for, I think, brain signals, I don't think, as far as I know, I don't think there's anything above like 64 hertz actually in, is it like 64 or it's like around there. It's like, yeah, it's like, yeah. So if you have any frequencies above 64 hertz in your data, it's probably not from the brain, it's probably from like something else around, because like there's a lot of like noise and electrical interference. So it's easy to just like get rid of that.
So it gets rid of everything above 64?
Mm-hmm. Yeah.
You said something about 120?
Yeah, like I don't think you should ever really have brain signals above 120, but anything above 64 generally isn't super useful anyway, so it's safe to just
Mm-hmm. Yeah.
On the lower end, how low can you go before it gets to other nodes? So 64 is the top end.
Yeah. I think a high pass is, I think you'll mostly probably, like I see low pass filters applied, but there's different like, I guess common like groups of frequencies which are associated with different things. So there's like the alpha frequencies and the beta frequencies. And one of them starts from like, it goes from like 0 to 1 hertz, and then there's one that's like 1 to 2, and then like 2 to 4 or something like that. But because it starts, there's one that's like 0 to something. I think all of them are like anything below 64 hertz or 120 hertz or whatever is like for the brain and useful, but you might not be interested in those brains because some of them are related to like emotion, some of them are related to, I don't know if you're thinking really hard or something like that, or you're reading or whatnot. So there might be like, I guess, parts of the brain or some, I guess, like activities going on that you're not interested in. Like if you just want to figure out like the emotion, you probably can just isolate like the frequencies that are associated with like emotion. Right, and there was nothing in the chat? Okay. Was anyone on the live stream? Okay, cool. All right, well, I think that's everything. I guess I'll be sticking around for a little bit if you guys have any more questions, but I think we could probably end the live stream. Okay, cool. All right, thanks for coming, guys.